Before I get started, show of hands, who here is super familiar with cryptocurrencies? Okay, perfect, because this is a talk to help people who aren't super familiar. Also, another show of hands, who is new to Elixir? Okay, so this talk is really for both groups, right? Trying to create a talk for people who are new, hopefully you get a better understanding of some of the things in Elixir, well, by way of Erlang, that make it really awesome. And what is this whole thing with crypto? So, yes, about me, I'm a developer at Carbon 5. I co-founded an organization called Elixir Bridge. For those of you that aren't familiar with what it does, we put on free workshops during the weekends for underrepresented folks in tech to help them learn Elixir and Phoenix. If you're local to San Francisco and interested, please talk to me afterwards. When I'm not doing that, and I'm not working at Carbon 5, I'm trying to get better at climbing rocks. It's photos from Bishop. It's in the Eastern Sierras, and it's one of my favorite places. Okay, so I kind of mentioned this, but what I want to talk about today, what is Bitcoin in the blockchain? What's all the hype about? Why do we care? How does it work? And then why might we try and build it in Elixir? So what is Bitcoin? Too fast. So if you look up a definition, you might see something like Bitcoin uses blockchain to implement a decentralized ledger for payments. So what does that mean? Really, you can think about it as a bunch of computers or nodes, right, all over the world, and each of them have a ledger, kind of like a bank ledger, right? And they work off of the same ledger. Or you can think about it really as a list with pieces of data, and each piece in the list points to a previous piece in the list. We also talk about it as this secure, semi-anonymous store of value. But I want to take a step back and think about, well, what do we mean by value? Like, what does it mean for something like Bitcoin to have value? So I want to take a look for a minute at value, but in the context of something that's more familiar, in the context of cash, money. So if you look at the definition of money, it's something that we can exchange for goods and services. We can pay our taxes in it. We can attribute debt by it. But really, what makes it valuable? And if we think about the history of money, up until really recently, cash, what we know as cash, was always backed by some kind of hard collateral, right? Generally precious metals, usually gold or silver, right? Even the first banknotes that appeared, I think in China in around 1000 AD, up to the first bank, non-nation state bank, which was created in Sweden in the 1600s, all backed by precious metals. And some of you might be familiar, or I guess a lot of you are probably familiar with the gold standard, right? Post-World War II, all the Allied countries got together and said, we are all pinging our currencies to gold. But why are these precious metals valuable? Any thoughts? So they're scarce, right? They're hard to find. They're durable, they're hard to fake, and they're arbitrarily divisible. But fast forward again, at least in this country, 1971, Nixon said, nope, we're not doing that anymore. Dollar's no longer going to be on the gold standard. It's going to be a fiat currency. But it's still valuable. So what made it valuable? Well, similar concepts, right? The central bank controlled the flow of money, so it's still relatively scarce. You can still pay your taxes in it. You can still exchange it for goods and services. But the last point, which is a little less nuanced, which is a little more nuanced, is that people were really betting on the future of the US economy, right? Betting on the idea that the US economy would do well, and then the dollar would continue to hold value. So back to Bitcoin, the big ideas behind cryptocurrencies, generally, is that for the first time, we're really doing value transfer over the internet completely digitally, not backed by some kind of hard collateral. So what makes Bitcoin valuable? Well, similar principles. There's a finite number of Bitcoin, so there's some level of scarcity. You can exchange it for goods and services. And while you can't quite pay your taxes in it yet, people are betting on the future. And there's also this aspect, right? People talk about it a lot, about it being, there's a level of anonymity and security. So before I talk about the blockchain and Bitcoin and how it actually works, I want to take a step back and look at security because it plays a big role. And if we look at the history of cryptography, especially in this country, it was really an admission of the government and the military for a long time. It was actually an admission of the military in the US until 1999, which seems kind of crazy. And in the 70s, with the advent of computers and with changing how we share information, early cryptographers actually started worrying about an individual's right to privacy. And they wanted to use cryptography to kind of help break the monopoly of the state. So fast forward again, 1992, a group of individuals got together, mainly three: Eric Hughes, Timothy May, and John Gilmore. John Gilmore later went on to start the EFF. They created a group called the Cypherpunks. They started a mailing list. They had hundreds of people on it. And the idea behind the Cypherpunks was they really believed in the importance of anonymity and that citizens have the right to privacy. And just because somebody wants anonymity doesn't mean that they have something to hide. 1995, he famously published the Cypherpunk Manifesto, and it said exactly those things. In the electronic age, we need privacy. We can't expect governments or corporations to do it for us. We need to do it ourselves. And the interesting thing about the Cypherpunks is they not only believed in the ideas, but they wanted to build the tools, to write the code to make those ideas possible. So many of the cypherpunks kind of made attempts at these early digital currencies. And a lot of them failed. Some of you may have heard of some of them. One of them that's more famous, Hashcash, was created by Adam Back. And there's a concept in it that Satoshi Nakamoto, the entity that created Bitcoin, uses called proof of work. We'll talk about that in a little bit. So fast forward to 2008, financial crisis. So there's a thread that had been happening in the cypherpunk community that kind of gets revitalized when everything crashes. There needs to be an alternative store of value outside of the government, outside of a nation state. 2009, coincidentally, Satoshi releases Bitcoin. Now, it's unclear whether or not he was a cypherpunk or the entity that is Satoshi, because we don't know who this person is. It's unclear whether he's part of the cypherpunk community, but he definitely took inspiration from it. And if you look at how he defines Bitcoin, right, it's essentially an easy way to securely transfer transactions anonymously without the need for a middleman. And this kind of hit on a lot of the cypherpunk ideas because it's decentralized. So there's no single point of failure, but there's also no single source of control. And it allows for anonymity. So how does it work? Well, I mentioned it's a decentralized network. So you have computers essentially, or not computers anymore really, but the idea initially all over the world participating in this network. Each of them has essentially a copy of this list that has pieces of data on it where each piece points to the previous piece of data. And it communicates via gossip protocol. And I thought this was an interesting analogy of how the gossip protocol spreads information, similar to a social network or how epidemics spread. But really the idea is a node sends messages to its peers, which send messages to its peers, and eventually those messages disseminate through the network. It might look something like this. So before I talk about actually how you might send a transaction, how it gets validated, added to a block, I want to take a moment and talk about asymmetric cryptography, which Bitcoin uses. Really, it's just talking about public and private key pairings. And the idea here is that if I'm sending, let's say I want to send Ben, again, let's say I want to send Ben 5 Bitcoin, right? I can create a transaction. I'm going to sign it with my private key, but send that transaction along and send my public key with it so that nobody can tamper with that transaction unless they have my public key. So it allows for a secure way to send transactions on the network. And it's important to note that in Bitcoin, there's no concept of an account. Let's say you went on Coinbase, you spent some money, you're like, okay, I now have 3 or 4 Bitcoin. There's no place that says, there's an account that says I hold these 3 Bitcoin. Remember, it's really just a ledger of transactions. So there's once that happens, once that transaction's created, it gets sent out onto the network, and there's going to be some place in the ledger that says, there's going to be a transaction written to the ledger that says, I have 4 Bitcoin. Now let's say I want to send Ben another Bitcoin, right? I have 4, and I want to send him another one. He's going to get really rich from Bitcoin. I'm going to need to create a new transaction. So I take my old transaction as an input, and I create a new transaction that says, I'm sending Ben 1 Bitcoin, I'm sending myself back 3 Bitcoin. And we call these unspent transaction outputs. So when you use a transaction to create another transaction, that initial transaction no longer becomes valid. And so what happens is, so we send a transaction onto the blockchain, right? Block picks it up, and it validates it, right? It takes the public key, decrypts the transaction. And then it rolls through all of the transactions in the ledger to check that that transaction is valid. Because in the ledger, it'll say, let's say I started with 4, and then I sent somebody 1, and I now have 3. If I try to create a transaction, another transaction to write to the ledger that says, I want to send somebody 6 Bitcoin, it's going to be invalid because the ledger no longer reflects that I actually have that many Bitcoin. So if the transaction's valid, it will get added to the block. So how do we add transactions to the block? So in the example that we're going to look at later when we build a version of Bitcoin, we're using one transaction for simplicity. But really what happens is each block can store about 1 megabyte of data. So it'll take as many transactions as it can fit, and it'll start essentially hashing them together in pairs all the way up the tree, in what's called a Merkle tree, until you receive a Merkle root. So you do that for really 2 reasons. One being, in a distributed system, there's really no global sense of time. And so it allows for some sense of ordering when we're talking about these transactions. And the other really is that we know when we're hashing, and we're using SHA-2 to hash these transactions, that if the content that you're hashing, if you change it ever so slightly, the hash that gets output is drastically different. So it really prevents anybody from tampering with the transactions. And a node can ping another node and say, hey, it looks like I have a different leaf here. My hash looks slightly different. What do you have? Because the root hash, if you change any nodes in the tree, will be drastically different. OK, so adding transactions to a block. How do we actually add blocks to the blockchain? Excuse me. So this goes back to that concept I was talking about in Hashcash that Adam Back invented, called proof of work. So nodes in the Bitcoin network always work off of the longest valid chain. But if it's really easy to add blocks to a chain, it's really hard to determine who actually has the longest chain, what chain should people be working off of. And Satoshi decided, well, maybe the nodes need to do some work in order for this to happen. So that it's slower to add blocks, and it's easier to kind of figure out who has the longest chain. And this proof of work is really just solving an arbitrary computational puzzle. So every network, the whole network as a whole, has this global work factor. And what that is really the level of difficulty for solving this computational puzzle. And all the puzzle is solving a hash that has a certain number of leading zeros. So let's say we have a work factor of 4. We're going to have a hash. We're going to need to solve for a hash that has 4 leading zeros. What content do we use to solve that? So we take our root hash, all the transactions that we've hashed. We take the hash that points to the previous block. We take our timestamp, and there's some other information. And then we have this nonce, which is really an arbitrary value that gets incremented. And we hash those together. And this happens over and over and over again, until we've solved the proof of work. And once we've done it, we've mined the block. We send that out to the network. And other nodes on the network can take a look at our block. And because our block is using a hash that was created by the previous block, the nodes, when they receive the new block, can see if it's valid. If it's valid, they will add it to their blockchain and start working off of blockchain length h. And remember, when they're validating, each block creates a hash. And the next block is using the hash that the previous block created to point to that block. So you can go through every block in the blockchain, which is what they do, right, and make sure that all of the blocks are actually valid, because they have the right hashes pointing to the previous block. So what did this do? What problem did this proof of work solve? Well, it solved 2 things. First, it gave the nodes in the network a way of agreeing on how to add blocks to the blockchain. And the second problem was because whoever kind of is able to add blocks to the chain kind of controls the chain for that period of time. And when Satoshi released blockchain, he assumed, it's not really the case anymore, but he assumed that computers had equal hashing power. And if they had equal hashing power, they had equal probability of adding blocks to the chain, and so nobody would have, there would not be uneven control over the network, right? Everybody would have an equal probability of mining blocks and adding them to the blockchain. And this idea of nodes agreeing to always work on the first blockchain of length h that they hear about is called Nakamoto consensus, or Nakamoto consensus. One last point that I want to make before we start talking about Elixir is that everything in the blockchain is probabilistic. There's really no sense of finality. So we assume that the block is valid. And really the rule of thumb is once a block gets added to a chain, kind of wait for 6 more blocks to get added. And then you can be confident in the fact that the block that you are adding is valid. It's not really going to get rolled back, or no one's going to try and fork before that. So why Elixir? Or why think about building a version of this in Elixir? Well, Bitcoin uses the blockchain to implement a decentralized ledger for payments. Nodes are sending messages using the gossip protocol. So we need a decentralized system, it's concurrent, and communicates via message passing. So to many of you, this might sound familiar. So before I go into how I kind of implemented this, and keep in mind this is kind of a contrived version, there are definitely security concerns and things that you would not want to run something like this in production, but to give you an idea of how Elixir and leveraging Erlang makes it really easy to implement some of these protocol like this. So first, I really want to take a quick look at how message passing works in Elixir. All the work that gets done in Elixir, any code that's run, gets run inside of a process. And they're isolated from each other. And you can run hundreds and thousands of them at a time. They're really lightweight. And they communicate with each other via message passing. So as an example, a module, we're subtracting things. How do we actually call a process? Call a function called spawn. We give it a module name, function, and arguments, and we receive back a process ID or a PIN. Now we know that these processes communicate via message passing. So how do we do that? Well, we have 2 functions, right? Send, where we can send messages to a process, and receive, where we can process incoming messages. So just a quick example. A module called greet by name. And receive, we can implement our receive function, which is going to match against the arguments that come in, and if they match, we will get output. So we can send to our process ID. If it matches, we get output. Otherwise, we don't. We also want a way of knowing whether that process is up, right? Once we start building our blockchain, we're going to need to know the state of our blockchain. Is it working? Is it sending out messages? What's happening? So a way of monitoring that. So Elixir is really easy to link to another process. We have a module called connection. We're going to exit or force the module to exit. So notice that if we spawn a process that we're not linked to, we receive back a process ID, but we don't know that what happened. It died, and we have no idea. If we use spawn link, which allows our current process to link to that process, it blows up and it kills our current process, and there are ways of trapping exits and making sure this doesn't happen, but the idea is we know what's happening. And we're also going to need some way of maintaining state. We're going to use, for this purpose, we are maintaining our blockchain state in memory. And so we're using agents. And agents are essentially an abstraction around background processes that maintain state. And they take either a named or anonymous function, and the return of that function becomes the state of our agent. And it's really easy to update the state and retrieve it. And for us, since the ledger is additive, we're really just adding to our list of blocks. OK, so back to the blockchain. So now we've talked a little bit about processes, how they communicate, how we might monitor them. But we might need slightly more sophisticated behavior, right? We need some more sophisticated monitoring. We probably need something to handle client-server interaction as nodes are sending messages to each other. So we are going to leverage OTP, right? It stands for Open Telecom Platform. It's a library with Erlang. And really what it does is it provides us a framework that has a set of modules and standards that make implementing this kind of behavior really easy. Okay, so let's start building. We're going to start with transactions. So take a look at our transaction module. We are going to create a transaction. It's going to have a struct. And really, every transaction we send is going to have a to, which is the public key that we are sending to, from, which is our public key, an amount. And then we're going to sign our transaction with our private key. So we can sign. And we'll also be able to validate transactions. So when we receive a transaction, we're also going to receive a public key for that transaction. We can decrypt the message, see the transaction, and then roll back through all of the transactions in our ledger to see if that transaction is valid. Okay, so we have transactions. Now we need to somehow build a chain of blocks. So we're going to start with a single block. The block module, also it's going to have a struct. It's going to have a nonce, which is that random value that gets incremented in order to solve the proof of work puzzle. It's going to have a hash that's pointing to the previous block, and then it's going to have a transaction. And for our purposes and for keeping it simple, we're going to have one transaction. And really what happens, we're going to call create, and we are going to hash together, right? We're going to solve this proof of work puzzle, hash together the previous hash, our transaction, and our nonce over and over and over again until we solve the proof of work puzzle. So this is really computationally intensive, and I did it here in this process. But in the next iteration, and as I build on this, I either want to try and pull this out into a separate process and maybe parallelize it to see if it's more efficient. But really, an interesting option that I've been thinking about and was talking to actually Sunny, who's speaking right now about, is pulling it out into a natively implemented function and doing the hashing there and then sending it back to this process using Rust. Because it seems like that might be more efficient, because this part does get very computationally intensive, especially when the work factor gets really high. Okay, so we have a block. How do we create a chain? Well, we're going to create a blockchain module. And it's going to have a couple attributes, right? The work factor, which I mentioned. How many leading zeros do we need to have on our hash in order to mine that block? A block reward, and I forgot to mention this earlier. Every time a node mines a block, they get a certain amount of Bitcoin. In this case, our block reward is 100. Right now, the Bitcoin reward for mining a block is 12.5 Bitcoin. It started at 50, and it halves every so often. As the Bitcoin chain gets longer, the reward gets smaller. So we're going to have a struct. It's going to have a list. We're going to call blocks, and then our public key and our private key. So remember, our public key is really our identity on the Bitcoin network. When we're sending messages and transactions, that's how other nodes communicate with us, is via our public key. So we'll have an initial state function, and we'll return a struct with those values. And we're going to store our state in an agent, right? We're going to store this list of blocks, in an agent. So we just call agent.startLink. We pass in our initial state function, and we'll have that struct. We want to keep an eye on this process, right? We want to know if it's dying. If it does die, we need to restart it, et cetera. So we're going to add a supervisor. Supervisors are specialized processes that are used really just to monitor other processes. And this makes it really easy to add fault tolerance to our application, right? As soon as our child process dies, the supervisor is able to restart. So how do we set this up? So in our application.ex file, which runs when we start our app, we pull in the use supervisor behavior, and we call supervisor.startLink, pass it some arguments. The first argument is a list of tuples, and each tuple takes a module, initial arguments. And then there are various strategies. The strategy that we're using is really one-for-one, so if our process dies, restart it. And then we give our supervisor a name so we can reference it later. And I think James mentioned this earlier, but supervisors need to know how to start the child processes. And so we define a function called childspec, which tells our supervisor how to start the child process. So to look for start, it'll say, OK, I need to call the startLink function. To restart it, we set it to permanent, so it's saying really just always restart if the process dies. Supervisors make fault tolerance really easy, and that's kind of what we want in our distributed blockchain. So let's look at the blockchain module again. We're going to add Every time we get a transaction, in our case a single transaction, we're going to try and mine a block. So we're going to check if the transaction is valid, and if it is, we're going to mine a block and add it to our blockchain. In this case, we have our agent that's storing essentially just a list. Really, that's kind of all it is. And because it's really just additive, we're just going to continue adding blocks to the head of our list. So we update our blockchain, and then we need to send it out. We've done it, we've mined a block, we have transactions, but we need to send it out to the network so other people adopt the new blocks that we've been adding, otherwise it doesn't work. So we need some kind of client-server interaction so that we can send requests and process to, again, reach into OTP, which provides us with a behavior module for doing this. It's called GenServer. It starts with generic server. And it does so by allowing us to implement a series of generic callbacks. We can choose which ones we want to implement. And so to create a GenServer, we're going to pull in that behavior. We call GenServer.startLink, give it our module name. It takes an init callback. And really, we're starting with a struct. It's really just going to be our process ID as the ID, our list of blocks for the blockchain, and a list of UUIDs. So every message that gets sent on the blockchain network has a unique ID. And the reason for this is when a node receives a message, it can then know whether or not it's already processed it or not. And if it has processed it, then it doesn't need to go through the whole process of either validating the transactions or validating all the blocks in the blockchain. And the way messages are sent on the blockchain using the gossip protocol, it's fire and forget. They're asynchronous. We're not waiting for replies. So we're just going to send a message and then assume that it gets there and kind of forget about it. And GenServer makes this really easy. For asynchronous requests, we call GenServer.cast. And the respective callback, right, in the GenServer that's going to handle that request is handlecast. So in this case, we are going to say, OK, we want to mine a block and send it out to our network. So we have that callback that's going to listen for those requests, match against the arguments. And then we're going to add a block, update our state, update our blockchain state, and send it out to our peers. OK, so we updated our state. But we also want to be able to see it, make sure things are going the way we expect. And GenServer makes it really easy to do synchronous calls as well. Right? So similarly to GenServer.cast signifies an asynchronous request. GenServer.call lets us do synchronous requests. The respective callback for that is handleCall. So we're going to say, OK, retrieve our state. And it'll match against the arguments. And I forgot to mention, but GenServer does allow us to maintain state. So the last argument in these callbacks is the state, the current state. So we'll return that. OK, so we added a block. And we're going to send it to our peers. But how are they actually able to receive it? We have a function we're going to send to our blockchain. And we're going to do another asynchronous request. Only notice this time is that we're sending to last time we just sent to a module and we passed in arguments. And this time we're actually sending to a peer. So GenServer doesn't really differentiate whether you're sending to other processes on your machine or other processes on other computers. If we give it the location of our peer with the full IP, it makes it really easy to communicate to other nodes. And then we have our handlecast callback for that. And really what's happening here is we're like, OK, have we already processed this message? If we have, we're not really going to do anything. If we haven't, we're going to look at the blocks and run through the entire blockchain, again, looking at each hash that points to the previous block, making sure that it's valid. If it's valid, and it's longer than the chain than we currently have, we're essentially just going to swap out that chain for ours. Again, this is a contrived example, but same idea. And we'll start mining off of that new chain. So I think I mentioned this earlier, and I actually can't remember if I did. But Satoshi, the idea of proof of work was also Satoshi wanted blocks to be mined kind of every 10 minutes was the idea. So the work factor adjusts on the network to make sure that that's what happens. So we essentially are saying we're going to have blocks mined every 30 seconds. And GenServer makes this easy to implement because if you don't specify the type of request that you're making, there's a callback that will actually handle those other requests for you called handle_info. So we're essentially going to say we're scheduling ourselves to send this message every 30 seconds. It's going to match against the argument schedule and send the message out, and then call itself again. And then to keep an eye on this process, because again, we want to make sure it doesn't die, we're going to use another supervisor. We just add that to our list at the beginning. And because it's a GenServer, it actually has a default child spec, so we don't need to define the child spec for that. OK, so we have a GenServer. We're going to send messages. We're going to send our blockchains out. But how do these nodes actually communicate? So if you're talking about processes on your machine, it's really straightforward. You're able to give your process a short name. And then you can call a function called node.connect and pass it the process name that you want to connect to. And if you connect nodes 1 to nodes 2 and 3, nodes 2 and 3 will automatically be connected. So you can see it makes it really easy to set up this kind of network. If you actually are on different machines, it actually doesn't take that much more work. You pass in a full name argument, and you need to give it a name and the full IP address and a cookie. So these nodes communicate via the TCP IP protocol, and so they use this cookie as a sort of low-level authentication. So you have two nodes connecting with different cookies. I actually think there's a way of configuring that, but initially they won't be able to connect. And again, very contrived version. There are definitely security concerns. You would probably want to be running this with TLS, not just like randomly communicating messages across nodes, but just to prove the idea. So let's try it. I'm going to show you an example. Live demos are always a really good idea. So I have 3 processes. I actually tried to get it across machines. Tried to do this before across machines. The network here isn't really configured to let me do that. So I'm just going to show you on my machine. Let's see. I'm going to start these. Generating some keys. Come on. I'm going to go back here. Oops. I'm going to connect. And every 30 seconds. So this might take a second. But we should see these nodes starting to communicate to each other, and you'll see the UUIDs getting passed. And then if you actually pull the state from each of the nodes, you'll be able to see that eventually the whole blockchain actually switches out. So they're actually starting to create their own. We haven't actually processed any messages yet, but we've each kind of mined a block and started our own blockchains. And that initial block was really called the Genesis block. So you kind of start your own chain. Come on, maybe I should have set it to not 30 seconds. But this worked earlier, so we should see. Oh, yeah, here we go. So just trying to keep track of the messages. We see the new blockchains coming out. And all it really took was a GenServer and a couple of modules and an agent. So yeah, that's all I got.
Any questions? Is the code public?
It will be.
Thank you.
After this talk. Nope.
Anyone else? No? All right. Thank you, Anna.
Yeah, thank you.